High school science often presents the atom like this. A single spinning unpaired electron generates a magnetic dipole, effectively turning the atom into a microscopic bar magnet. If every atom with an unpaired electron behaved this way, the physical world would be unrecognizable. Consider the oxygen in the atmosphere. Every molecule is packed with unpaired electrons, yet the air doesn't clump together magnetically. As this diagram illustrates, those unpaired electrons are necessary for magnetism, but as the text box notes, they are not sufficient for permanent bulk magnetism. For a microscopic moment to become a macroscopic magnet, it must survive a multi-step quantum survival course. This is the magnetism gauntlet. It represents the 4 structural roadblocks that prevent most elements from exhibiting a net magnetic field. Roadblock 1 is thermal disorder. At finite temperatures, ambient heat acts as a disruptive force, tending to randomly spin and scramble electron alignments. This scale shows the competition between forces. On the left, thermal energy attempts to shake the spins apart. On the right, exchange coupling, a quantum interaction, tries to keep them aligned. When heat dominates, the result is paramagnetism. An external field can force a temporary alignment, but as shown here, that alignment disappears once the field is removed. This is the state of oxygen gas. Materials that survive the heat immediately face the second hurdle, neighbor cancellation. In many substances, quantum rules dictate that adjacent spins must point in exactly opposite directions. This state is called antiferromagnetism. As the equation at the bottom shows, a positive microscopic moment and a negative sum to zero. A material can possess perfect quantum magnetic order, yet exhibit zero net magnetization to the outside world, because its internal components cancel each other out. If the moments avoid cancellation, they encounter roadblock 3, where the physical architecture of the crystal fights the magnetic moment. Electrons contribute through spin and orbital motion, but surrounding atomic electric fields can suppress this, known as quenching. Alternatively, in metals, electrons may become itinerant, wandering as extended quantum states. To be magnetic, they must satisfy the Stoner criterion, otherwise the metal remains non-magnetic. The final hurdle appears even after a material achieves parallel atomic alignment. As shown in this graphic, the bulk material naturally fractures into microscopic domains. Within each domain, atoms align, but the domains themselves point in different directions. The material splits this way to minimize its global energy, avoiding the cost of a unified external field. Nature effectively sabotages macroscopic magnetism by forcing billions of perfectly aligned atoms to turn against each other and cancel out their collective magnetic field. Iron is one of the rare materials that navigates every stage of this gauntlet. This comparison highlights the difference. On the left, oxygen molecules remain randomized and paramagnetic. On the right, iron's exchange alignment overcomes thermal disorder, and its domains can be locked into a unified order. This results in true ferromagnetism. This panel addresses the relationship between individual moments and bulk magnetism. Large individual moments do not guarantee a strong magnet. Spatial alignment is the determining factor. The essential chain is clear. Unpaired electrons provide the raw ingredients, but exchange interactions and collective alignment decide the final result. Permanent magnetism requires billions of individual atoms to maintain a specific alignment, a state that occurs when a material survives the entire quantum gauntlet.